holography, there is a dictionary between conserved currents in the d-dimensional CFT and gauge fields in the ADS d plus 1. This is a sort of a basic element in the in this holographic dictionary, in this equivalence, and that operators in the quantum field theory are dual to fields in the bulk, and in particular the operators corresponding to conserved currents are dual to gauge fields in ADS d plus 1. And the simplest example of this is that the energy momentum tensor in the CFT corresponds to the graviton of the gauge field, of the metric field in ADS. This is the simplest example of this, but you can have, for instance, other conserved currents dual to usual gauge fields in ADS. So this is a very general part of the dictionary, and it comes essentially because fields in the bulk act as sources for the operators on the boundary, and if you have an operator which is a conserved current, that then the coupling, the usual H mu nu, T mu nu, or A mu J mu kind of coupling implies that the conservation of the corresponding currents imply a gauge symmetry for this. This is sort of inverting the kind of argument that you saw in the morning, in which gauge symmetry implied a conserved current, but you can sort of invert the argument in some ways, and in this dictionary, the conservation of these currents implies sort of a gauge symmetry for these dual fields. So this is a part of the dictionary, and in many CFTs. So in general, in the CFTD, in the free limit, when they become free, there are additional conserved currents beyond the spin 2 current. So any free theory, even a free scalar field theory or a free fermion field theory, has an infinite number of additional conserved currents, which are very simple to write down. So for instance, in a free theory, you can write down in some with some combination of derivatives acting on the left and the right, you can write down bilinears of these. You can write down bilinears of the scalar field with derivatives sprinkled on both of them. So these arrows are indicating that they act on these. So I'm just writing it very sketchily. There's a linear combination of such terms with some number of derivatives acting on this, some number of derivatives acting on that with precise combinatorial coefficients. And these are conserved by the by using just the by using just the equations of motion. For instance, if you have a massless scalar field, then when you take the divergence, you'll get a contraction. You'll get at least one term which involves box phi, and therefore by the equations of motion that box phi is 0, these are trivially conserved. So you can write down many such conserved currents in the free limit, and in this equivalence, the equivalence is of course in general for interacting conformal field theory, but it extends to the limit where the CFT is free. So you would expect by this dictionary that these conserved currents, these higher spin conserved currents, would correspond to some higher spin gauge fields in the bulk, generalizing this dictionary. But these would be massless only in this limit where the CFT is free, and this limit, this free limit, in terms of this the CFT coupling, if you call that lambda, this equal to 0, and this sort of corresponds to the tensionless limit in ADS. The dictionary between the parameters in the string theory and in the CFT tells you that when the coupling is 0, that's like the tensionless limit. So in the tensionless limit, you have a subsector of the CFT, which namely a set of operators of the CFT which are conserved currents, and therefore there must be a subset of fields in the string theory in ADS which correspond to massless higher spin gauge fields, so sorry, I should have, this phi is different from that phi. This is just some scalar field in the CFT. These are fields in the CFT. This phi is a field in the bulk, like the Vasiliev fields that I wrote down earlier. So this is roughly the reason why you can make this more precise in particular cases, but this is roughly the reason why you expect the Vasiliev theories to be a subsector of the string theories in this tensionless limit. So holography tells you that that the tensionless limit is the one in which you restore these additional gauge symmetries, which you couldn't see in flat space. In flat space, you could see at very high energies. So high energies is the same as sort of taking effectively a tensionless limit, because the energies are much higher. The energies there were taken to be much higher than the string scale. So the effective dimensionless parameter, it's effectively as if the string were tensionless. But the holography gives a much more precise realization of that idea over there, because you see that you have a whole one-parameter family of CFTs dual to the string theory, but in a particular limit, you get a set of additional massless fields, which are sort of, so in some ways, this is the point at which the symmetries are restored to a very high extent, and you have this Vasiliev symmetry. So this is the connection between these two motivations, that the string theory symmetries in some ways are realized in an unhiggsed fashion in ADS spacetimes, where the Vasiliev symmetries are more manifest. So that's the motivation. Yes.
For non-zero coupling lambda, there is no way of modifying the current so that they are conserved.
No, there is no way. Well, in any CFT higher than 2 dimensions. So in 2 dimensions, as we will describe, you can evade this Coleman-Mandula theorem again. In fact, the Coleman-Mandula theorem itself, when the authors developed it, they showed that in d equal to 2, their theorem doesn't apply for 2-dimensional quantum field theories. There, even when the coupling is non-zero, you can have conserved currents of higher spin. And there are many known examples of that, and I will be talking about some of them in this theory. But for any quantum field theories or conformal field theories higher than in 2 dimensions, when you turn on the coupling, the higher spin symmetry, there are no exactly conserved currents. One interesting thing, and this was systematically studied by Maldacena and Levkovich, Maldacena and Zhibodev a couple of years ago, they showed that the symmetry is just slightly broken when you turn on the coupling, and by using that, the Ward identities for a slightly broken conserved current, they could get many non-trivial consequences out. So even when you turn on the coupling, you can break the symmetry in a sort of a mild way and get still many consequences out of that. So
it is something like partially conserve the current of the old days.
In some ways, yeah, you can think of it like that. It's because it is sort of spontaneously broken or Higgs. You can derive consequences from, even though it's broken, you can derive consequences from that. Yeah, it's in the same spirit. Yes?
So you talked about the correspondence between free limit and tensionless limit, but is there any restriction on the 1/n collections? It's beyond the planar limit?
Okay, so yeah, I haven't discussed that. So there is, he's alluding to the fact that there's typically in this correspondence, there is an additional parameter n, which is the rank of the gauge group, which you have to take large to make the correspondence with the classical string theory. You talk about the large n expansion of this to make the correspondence with the string theory. So there is the parameter 1/n that corresponds to the string coupling in the bulk theory, or if you wish, the G Newton. So 1/n plays the role of the Newton's constant, and you need large n to talk of a classical theory of gravity in the bulk. But this statement that I made is true even for any finite n. You can talk of the full quantum theory as well, because yeah, these kind of conserved currents exist even at finite n. But what you're referring to, so in addition, if you take n to be large, then you're restricting to the classical limit in the bulk, and that's what you need actually to look at, say, the Vasiliev theories, because the Vasiliev theories, we know them only at the classical level. No one has succeeded in telling us how to quantize them or anything. So we have a definition of the Vasiliev theories only at the classical level. So when we actually construct duals, we will be taking n also very large to describe the Vasiliev, to match with the Vasiliev theory. Okay, so after this sort of very general long introduction, let me try to specialize and focus on a particular case of all this, which will make these very general considerations sort of more concrete, so that we can sort of see precisely what we mean by everything that we have said so far. So this will be like a good, as I said when we when talking about holography, what we are looking for are tractable examples, or toy examples, and that's the standard approach that any physicist takes when you want to understand a complicated problem. For instance, when people wanted to understand phase transitions, it was very useful to have a solvable example like the 2D Ising model, which helped it's a simple toy example, but it's solvable, exactly solvable, and therefore you learned a lot about critical exponents and so on, and that helped in developing the full theory of phase transitions. So similarly for holography, you need simple examples, as I said, tractable examples, and so we will focus on one which has the virtue of being very simple, very explicit, it's much simpler than, so we will talk about example in three-dimensional anti-de Sitter space, which will be simpler both because you can visualize it. It is exactly this diagram that I drew over here, and dual conformal field theories, which are explicit. And this also has the virtue that the corresponding Vasiliev theories will be much easier to construct in ADS3. So I said that the equations of Vasiliev are very complicated, and indeed that is true. There's a lot of machinery you would have to develop, and I wouldn't be able to do it in 3 or 4 lectures. But in the ADS3 example, things are much simpler, and so hopefully you will be able to appreciate that. So that's the reason that we will now focus on higher spin theories on ADS3 and their duals. So in the rest of these lectures, I will focus on this example to illustrate things. So to do that, let me first tell you a little bit about gravity, ordinary gravity or Einstein gravity in ADS3, and a slightly different formulation of that, which maybe you have not seen before. So what we will start off with is the so-called Chern-Simons a formulation of 3D gravity due to Achikaro and Townsend and also Witten in 1980s. Oh, before I go on, let me also give you some set of references which maybe you might find useful. So there's a general review by Simon Giombi and Shi Yin on highest on holographic duals to higher spin theories in general. This is in 1208.4036. But they focus, they give a nice sort of an overview of the Vasiliev equations, but then focus mostly on the case of ADS4 and dual CFT3, which is also has many interesting features. So you can look at their review for that. There's a review that I wrote with my collaborator Matthias Gaberdiel, which appeared around the same time. This is these lectures will be sort of based on some of the material there. So this is focuses on the ADS3 and the CFT2 case. I will also talk a little bit, maybe if I get time, about black holes and other solutions for higher spin theories in ADS3, so that's covered in a nicely summarized in a review by Ammon, Krauss, Perlmutter, and Michael Goodpearl. So they were the people who uncovered some of these new solutions, and so this is in the review over here. So as you can see from the numbers, they're all together. That's because they all appeared in the same Journal of Physics special issue. So these were sort of somewhat coordinated reviews, which between the three, I think they cover various aspects of the subject. Yeah, so at least for sort of an introduction, this wouldn't of course cover some of those things after that, but at least it will give you a good introduction to the subject if you're interested in pursuing it further. Okay, so let me explain to you a little bit in the remaining. I mean, let me just get started at least on the. So I have till 3:30. Yes. Yeah. Let me just get started on this Chern-Simons formulation of gravity in ADS3. So you know that gravity can be so the metric-like formulation in which you write down normally Einstein's equations, etc. Is of course the most common one, but there is an alternative formulation, the so-called frame formulation of general relativity, in which the basic variables are the so-called field binds and corresponding spin connections. So what are these? I mean, I don't know if you have seen this, but I'll just briefly tell you a little bit about this. So instead of talking about a metric as your basic variable, you replace it by a so-called one form, taking values in SO, so if you are in d dimensions in SO d minus 1, comma 1, so we will be in 3 dimensions, so we'll focus on the SO 2, comma 1 case. So this is in general, but since I talked about ADS-D plus 1, let me keep to that notation. So here SO 2, comma 1, which is the sort of the tangent space to or the local Minkowski symmetry. So this A, so these are the SO d, comma 1, SO 2, comma 1 indices. So in d equal to 2, that is ADS3. This field bind formulation exists for any, it doesn't have to be in any ADS spacetimes, but to just keep to the 3-dimensional case, A goes from 1, 2, and 3. We'll take, there are 3 tangent space directions. So mu is the coordinate index. And this is the SO d, comma 1 tangent space. Index. So mu, of course, also goes from 0, 1, 2, or 1. So yeah, if you wish, mu you can take to be 0, 1, 2, the usual coordinates. And A, so the Latin letters will refer to the tangent space indices, and the Greek letters to the coordinate space indices. And this field bind is basically like a gauge field for the metric. So the metric locally can be written as E mu A of x, E mu A of x sum over A. So basically, it's a sort of E can be viewed as some kind of a square root of the metric. But of course, you see from this that there's a sum over A, so this doesn't uniquely specify the field bind. There is if I find one set of E's which satisfy this, you can find you can rotate each of these E mu A's by a local Lorentz transformation or a local tangent space transformation. So E mu A of x goes to some lambda AB of x, E mu B of x. So this is a local Lorentz transformation. So this is invariant under these local Lorentz transformations. So these act like some kind of a, so that's why you can view this as some gauge field of the SOD, 1 tangent space, or SO2, 1 tangent space. That's what this frame formulation basically does. In this frame formulation, you also introduce the field bind and one more quantity, the sort of the spin connection. So in this frame formulation, there are two ingredients which one is this field bind, and then there's the spin connection, which is an antisymmetric in the two indices A, B, and so it has two tangent space indices, so it's an antisymmetric rank 2 tensor in the tangent space indices, and with one coordinate space index. And the spin connection is a priori an independent variable, unrelated to the field bind. But if you demand that the so-called torsion vanishes, then you get a relation which relates this omega mu to this E. This is very much like the Christoffel connection that you normally study in general relativity, is obtained by demanding the covariant conservation, the fact that the metric is covariant derivative is 0. So the connection is a priori an independent object, but if you demand in that case as well, if the torsion is 0, then you get uniquely the Christoffel connection, which is related to the derivatives of the metric in the usual way. In this frame formulation, it is similar. You have this other object which is like the connection. So you see that it also has three indices like the usual Christoffel connection does, but it's distributed differently. There are two tangent space indices and one coordinate index. And there is a zero torsion relation which enables you to, which I will write down tomorrow, I guess, which relates this omega to the to E. But in this frame formulation, these are independent variables, and that's convenient for some reasons. By the way, if you ever going to study spinors in general relativity, fermionic fields in general relativity, you have to use this formulation because that's how you can define the curved space spinors and their coupling to gravity through the spin connection. So that's why it's called a spin connection, because it was sort of originally introduced in that context for spinors. In any case, so this is very general. So all this is very general, but in 3 dimensions, and that's what these gentlemen observed. In 3 dimensions, there is a additional simplification. And you can define omega mu A with one index as basically epsilon A, B, C, omega mu B, C, where this epsilon is the usual epsilon tensor that you have in, so in 3 dimensions, the epsilon tensor has 3 indices. So you can, and since it's anti-symmetric,